Okay, folks, we get to start with atomic properties of transition metals. And our focus is going to be electron configuration. Why? Well, because to understand transition metals and their ability to be reactive or exhibit all these different colors, for example, we need to know how many electrons occupy their orbitals. So electron configuration is essentially basically a way for us to predict chemical behavior and properties because it's going to help us describe how those electrons are distributed in those atomic orbitals. Let's go ahead and see how we do that. Well, first, with the main group element, we mainly will use the off-bow principle, right? And the off-bow principle will tell us that, oh, okay, we're going to be filling our orbitals as we propose from S to P, and then go across from each period, D here, P orbitals, and then we have the F orbitals here. We're going to continue to fill based on that off-bow principle. And the arrangement of electrons are going to influence how atoms form bonds and, of course, interact with one another. Now, to write the electron configuration, we're going to have to use a specific notation that we have for electron configurations, and we'll also talk about the condensed form, which is what we'll use mainly for Chem 102. So first, the electron configuration is always going to be written with a principal quantum number, and normally we denote that as N. Okay. We're also going to show us the shape of the actual orbital in, or called the sublevel. This is S, and we can have S, P, D, and F orbitals. And also it's going to tell us the number of electrons within that particular orbital sublevel. Okay. You can also write the condensed formula that I was telling you about, which mainly has a noble gas configuration in parentheses, and then whatever the rest of the electron configuration would be for that particular element. Okay. And then finally, you can write orbital diagrams just so you can actually see how the electrons are going to be paired or unpaired in each orbital. So let's say we're going to focus on the d orbital. There's going to be 5 different shapes for the d orbital. Okay. And these are going to be our d orbitals here. And if each d orbital had 1 electron, we can say that we have 5 unpaired electrons here, for example, and those unpaired electrons have the ability to form potential bonds. Now, as we go higher, we're going to learn more about the details of this potential colors and magnetism that can actually happen with electron configuration. And we'll get that in multiple videos later. Now let's focus specific on the transition metal portion of electron configuration. So mainly we're going to be using the S and D orbitals. We also can use the F orbital. So for the F orbital, meaning that you're going to have 7 different orbital shapes, okay, and you can have a maximum of 14 electrons, versus the D orbital, which has 5 different orbital shapes and a maximum of 10 electrons, and the S orbital, which has 1 orbital shape and a maximum of 2 electrons, for example. Okay. Also, there's going to be different electron configurations for the D block and also period 6 and 7. So we kind of have general formulas to help us understand really how to write any electron configuration for any of their transition metals, because they don't, again, follow the same kind of rules for everything else. So for example, if you have a D block configuration, meaning periods 4 or 5, so here are the formulas. With periods 4 and 5, the formula is going to be your noble gas in brackets, NS squared, meaning the period 4 to 7, S, which is going to be your orbital with 2 electrons filled in it, N minus 1, which is going to be your period numbers 4 to 7 minus 1, and then orbital D raised to the power of X. And that X can be anything between 1 and 10, right? Because we're talking about the D orbital, so it has up to 10 electrons. Again, the formula is going to be your noble gas in brackets, NS2, N minus 1, D raised to the power of X. So for example, if you're looking at scandium, then you would have your noble gas, which is going to be your argon. You would have 4s2 because it's in period 4, so my N will equal to 4. N minus 1 is going to be 4 minus 1, which is 3. And then the D electron is going to simply be 1. So it's going to be 4s2 here, and then 3d1. So you can look at the periodic table. You also can use the amount of electrons that we see for scandium as well, which is 21 electrons. So argon has 18 electrons, 19, 20, 21. So this is going to be the electron configuration for a period 4 transition metal. Let's try one with a period 6 or 7. So let's use hafnium. So hafnium is going to be in period 6. And again, hafnium is here. Period 6, that means it's going to be 6s2, but first we need our noble gas. Our noble gas here is going to be neon. We're going to have 6s2, okay? 6 minus 2 is 4, so that's going to be 4f14. And then dx is going to be how many electrons are in the d orbital. For hafnium, that's going to be d2. Okay. So that is our, but of course I forgot my actual number here. So let me go ahead and erase this. This should actually be 5D2. Because right here, let me go ahead and erase that. Go ahead and make sure you make this large change here. What's out there? This is actually n minus 1 dx. Okay, so we were in, for hafnium, we were in period 6. That's how we got 6s2. And then 6 minus 2 is 4. That's how we got the 4 here. F14. And then n minus 1 is 6 minus 1, which is 5. That's how we got the 5 here, D2. I apologize. I did forget about the F1 there. Also did forget about the n minus 1 for this one too. So it's actually an n minus 1 here as well. N minus 1, n minus D, that's 2 power 10. Okay. I do apologize for that. Trying to rewrite it perfect. Okay, folks, so that's just a couple of examples of scandium, hafnium, and then for the exceptions, you'll basically be going through, but instead of filling in for chromium and molybdenum, for example, instead of filling in the entire s orbital, you actually would have your period here, s raised to the power of 1, n minus 1, d to the power of 5. Okay, this is one of the exceptions to make sure that we form stable compounds. More exceptions, copper and our silver. Other exceptions are gold as well. So you just want to follow those particular exceptions. As you're writing the electron configuration, it does make it a little bit easier when you see transition metals. When you don't see transition metals, you'll just basically follow the Aufbau principle or follow the periodic table like you normally would. Let's get into some more examples so that we can understand that first, when it comes to this, you just want to make sure you're locating things on the periodic table. And then you want to just make sure that one of the biggest things that comes along with transition metals, and make sure I highlight this, is that when it's time to lose electrons, okay, you're always going to lose those ns electrons first. You're going to lose ns electrons first. Okay, then you'll lose your d orbital electrons, and then you'll lose your f orbital electron. Okay, so that means when I'm going through, let me go ahead and get a new highlighter color. These ns2 electrons here, these ns2 electrons here, these ns1, this ns1, and this ns1, all these electrons are going to be removed first when you're thinking of ions, okay? So again, when you're thinking of any kind of ions, okay, let me make sure I'm writing this very clear. Erase all this. So when you're thinking of ions, you're going to lose the NF electrons first, okay, and then followed by d orbitals, and of course the f orbitals. So now the real goal is to put all this into perspective with some examples. Let's get to it. Okay, so for these examples, the goal is just to write condensed electron configurations for the following. So we have A here, zirconium, we have V3+, we have MO3+, and we have RE4+. Okay, so the first thing I want to do is just locate these in the periodic table. I have my zirconium here. I have my vanadium here. Of course, this is going to be period 4, 5, 6, 7. All right, just so that you can remember what this little periodic table is telling us, that information. Let's go ahead and find the other ones. Vanadium, boom, and then RE, boom. Okay, so now that we located everything like that, then we're going to ask ourselves, okay, we know that we have our general D block. We know we have our 6 and 7 period electron configurations and some of our exceptions. And we have to ask ourselves, do any of these kind of fit that mold, okay? So first things first, we have our vanadium and our zirconium here, our ZR, are both going to be in periods 4 and 5, okay? We also have our MO, which is also in period 5, but one thing we have to talk about here is it's in the same group as chromium, and chromium was one of our exceptions. So because MO is in the same group, we want to make sure that we are treating it just like we would chromium. Okay, folks, so just keep that in mind. Let's move forward. Now we have our RE, which is going to be in period 6. So we definitely need to use all 3 of our formulas. I will first just write down all my formulas just to make sure that I'm all in the right and have my head space in the right area. So again, you can just stop and use flashcards like in the previous information. You could use electron configuration, have all 3. Your general or period 6 and 7, and then your exceptions, and then use that as you're going along the path. Okay? Okay, so period 4 and 5, like we see for these three here, are going to be our noble gas, NS2, N minus 1, D raised to the power of X. But we do have an exception that we're going to be using for MO, which is going to be very similar to chromium, where we have our noble gas, NS1, N minus 1, D raised to the power of 5. Okay, folks? So that's what we have there. Now, for our period 6 group here, which is RE, we're going to be using our noble gas, NS2, N minus 2, F14, and then N minus 1, DX. Okay, folks? So that's what we're going to be using. Now let's go ahead and get into our other one. Okay, so this one I'm going to use for zirconium and vanadium. Let's start with our ZR. We see that ZR is going to be in period 5 here, so we can use our formula to basically get the electron configuration. Okay, so we're using this one here. Our noble gas is definitely going to be our krypton. Of course, you want to have a periodic table already out for yourself as well. Okay, since we are in period 5, the N is going to be 5s2. N minus 1 is 4, so that's going to be 4. D, and then where is that actually placed in the D block? So this is going to be 1 here, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So zirconium is going to be 2. So our answer would be KR in brackets 5s2, 4d2. Okay, let's move on to the next one. B, which is going to be the ion V3+. So anytime I see ions, I first go ahead and write V by itself or vanadium by itself, and then I go ahead and take away 3 electrons, starting with those NS electrons. So vanadium by itself is going to be our argon, you can see here, and of course get your periodic table. This is in period 4, so it's going to be 4s2. We can see and follow in this pattern. 4 minus 1 is going to be 3. This is 3d. And of course, where is vanadium in the D block is going to be 3. So it's going to be 3d3, okay? That's what normal vanadium looks like. Then I go back and I tell myself, okay, vanadium now has to lose 3 electrons. So first, these electrons are going to be gone. That's 2. And then 1 from here. There's 2 left over. So the ionic form of vanadium 3+ is going to be argon 3d2. So basically just keep everything that's left over. Next, let's do number C, which is molybdenum. So first we're going to get MO by itself. Again, we are in period 5, so that's going to be our krypton 5s1. So again, we're using the exception here. Remember, folks? 5s1. Now 5 minus 1 is going to be 4. So we're going to have our 4d, and then we have to count what molybdenum is. 1, 2, 3, 4 here. And instead of counting up here in D block, we're going to use our exception, which means that we're going to have 4d5. So this would be for our MO. Now we have to go further and get it for MO3+, is what the question asks. So first we have to get rid of our S group, which is going to be 1 electron, and then we need 2 more from here. So it's going to be 3 left over. I'll rewrite everything. Kr 4d3. Okay. Finally, we're going to go ahead and do the last one, which is Re4+. So again, I'm going to get Re. No exceptions. I just have to use the period 6 and 7 formula. So this is period 6. So I'm going to have 6s2. And then 6 minus 2 is 4. So that's going to be 4f14. Okay. Next, I'm going to do n minus 1, which is going to be 5. And then dx. So where is Re? 1, 2, 3, 4, 5. So 5d5. Okay. Now the next step is going to be removing however many electrons they want. They want Re4+, so I'm going to remove 4 electrons. First starting with the S, so that's 2 here, and then 2 from here, which is going to leave me 3. So I'm going to rewrite what I have here. Oh, and again, I just made a mistake as well. I forgot my noble gas here. Sometimes I'm just going fast and I forgot my noble gas. The noble gas here is going to be xenon. So I have my Xe, 6 Se, I'm tripping, Xe, okay, 4F14, 5D3 as our final answer. Okay, folks, sorry about the little mishap at the end. Now, don't forget to have yourself a flashcard moment so that you can move through this work a little bit easier, and it's easier for you to review when you are doing some homework problems.